welcome back to the deep dive. For this deep dive, we're going to be tackling Sylvester's sequence.
Okay.
And this one, this one, I can tell from the sources you sent that it really kind of sparked something in you.
It has.
Yeah.
It's a fascinating one.
We got encyclopedia entries, we got Wikipedia pages, and even your own notes.
Oh, yeah. I've been doing a lot of research into this one.
Clearly. So our mission, should we choose to accept it, is to unearth the coolest, most insightful bits from all this material.
All right. Sounds good.
And get this, we're going to uncover some seriously surprising connections along the way. We're talking ancient Egyptian fractions, proof that there are infinite prime numbers, even using the sequence to build complex geometric shapes.
Wow. I'm intrigued already.
Yeah, it's a wild ride, this one.
So where do we start?
Well, I guess the best place to start is with how it's built, right?
Right.
The sources keep mentioning products, which already sounds a bit intimidating.
Yeah, it can seem that way at first, but the core idea is really simple.
Okay, lay it on me.
So each number is basically the product of all the previous numbers in the sequence.
Okay.
And then you just add 1.
So it kind of snowballs as you go along.
Exactly. You start with 2.
Okay.
Then to get the next number, you multiply 2 by itself and add 1, which gives you 3.
Gotcha.
Then you multiply 2 and 3 and add 1 to get 7, and so on.
So the first few terms are 2, 3, 7.
43.
Oh, wow. 1807.
And it just keeps getting bigger. Fast.
Yeah, 1807 already feels like a huge jump. And hold on, I saw in the sources that there's more than one way to define this thing.
You're right. There's the product formula we just talked about.
Right.
But there's also a recursive formula.
Recursive, so that means...
Each term is defined based on the one before it,
instead
of having to look back at all the previous numbers.
Right. That makes sense.
In this case, the formula is subti 1 subti power 1.
Okay, so instead of looking back at all the previous numbers, you just need the one right before it. I can see how that would be useful.
Yeah.
Even if it still leads to some seriously massive numbers. Speaking of which, just how fast are we talking here? These things get huge, right?
Think doubly exponential growth.
Doubly exponential.
It's like exponents on top of exponents.
Okay, now we're getting into some serious math territory, so we're talking way faster than just your average exponential growth.
Way faster. There's even a closed form formula involving the constant e.
E? Like Euler's number.
You got it.
But you're saying even that becomes incredibly hard to calculate directly.
Oh, absolutely. You'd need a ridiculous number of decimal places for e to even come close to the actual values in the sequence.
Okay, I'm starting to understand why this sequence is so intriguing. But where else does this powerhouse sequence show up? Beyond just being a mathematical curiosity. I mean, my notes mention something about ancient Egyptian fractions.
Now, this is where things get really interesting. Ancient Egyptians, they used unit fractions, fractions with 1 as the numerator to represent all sorts of quantities.
Oh, so instead of using like 3/4?
They'd use a combination of fractions like 1/2 and 1/4.
Gotcha. So how does Sylvester's sequence fit into all of this?
Well, here's the mind-blowing connection.
Mm-hmm.
If you take the reciprocals of Sylvester's sequence, so 1 divided by each number, and you add them all up, you get 1.
Wait, are you serious?
Yeah.
You're telling me 1/2 plus 1/3 plus 1/7 plus 1/43 and so on, all the way to infinity equals 1.
Exactly. It's a remarkable property of this sequence.
That's wild. I never would have guessed that. So we're not just talking about some abstract infinite sum here.
Yeah.
There are real implications.
Oh, absolutely.
This means you could actually create finite Egyptian fractions for 1 using this connection, right?
You got it. For example, you take those first 3 terms, 1/2 plus 1/3 plus 1/7.
Okay.
They fall just short of 1.
Right.
But if you change that last fraction to 1/6, boom, it adds up perfectly.
Huh. So you're saying 1/2 plus 1/3 plus 1/6 equals 1.
Precisely. You can use Sylvester's sequence to create elegant and accurate Egyptian fraction representations of 1.
This is blowing my mind already. It makes you wonder if those ancient Egyptians were secretly math wizards, using this sequence without even realizing it. And what about that formula for the partial sums? The sources mention something about a really neat formula.
You're right. There's a formula for the sum of the first j terms of the series.
Okay.
And it's surprisingly concise. Sub subis that for own subi sub 1 or your 1 will sub g sub 1.
Wow, okay. I'm going to need a minute to process that one. But this is incredible. We started with a pretty simple rule, multiply and add 1, and now we're talking exponents on exponents, ancient fractions, elegant formulas. This sequence clearly has a lot more to offer. What about the connection to prime numbers? That was another thing that caught my eye in the sources.
Ah, yes. Prime numbers. It turns out Sylvester's sequence can help us prove there are infinitely many of them.
Really? I thought mathematicians had that one figured out ages ago.
They have. But Sylvester's sequence offers a really unique and elegant way to demonstrate it. Remember how we talked about every two numbers in the sequence being relatively prime?
Relatively prime meaning?
They share no common divisors other than one.
Right, right. So how does that prove there are infinitely many primes?
Well, think about it. If each prime can only divide one number in the entire Sylvester sequence, and that sequence goes on forever.
Then there must be infinitely many primes to keep those numbers relatively prime, right?
Exactly. It's a pretty neat proof, wouldn't you say?
That's actually really cool. Okay, so this quirky little sequence isn't just about big numbers. It touches on some fundamental concepts in number theory. But I also noticed that my notes mention there's a lot we don't know about these numbers, even with all this knowledge.
Yeah, that's the fascinating part. We can create these numbers, we know lots of their properties, but we still don't know how to factor most of them completely into their prime factors.
Seriously. I thought with computers, prime factorization was pretty straightforward these days.
Well, even with computers, the sheer size of these numbers makes it incredibly difficult. The Wikipedia page you sent over even has a table showing how few factorizations are known beyond the first few terms.
So we can define these numbers, we know a lot about them, but we can't even break them down into their basic building blocks. That's crazy.
It really is. And it gets even more intriguing when you consider that no one has ever found a square number in the sequence.
Wait, so no one knows if a square number is even possible in this sequence?
Exactly. It's an open problem in mathematics.
A potential square number hiding somewhere in the vast expanse of Sylvester's sequence. That's a true mathematical mystery. So let me get this straight. We've got this rapidly growing sequence. It's connected to ancient fractions. It helps prove there are infinitely many primes, and he's still holding on to some prime factorization secrets. This is blowing my mind. What else can this sequence do?
Well, prepare to be surprised. Sylvester's sequence actually pops up in some areas you might not expect, like constructing complex geometric shapes.
Wait, so this seemingly abstract mathematical sequence has real-world uses?
You bet it does.
I'm definitely intrigued. Tell me more. Okay, so we left off talking about real-world uses. Where does this sequence actually show up?
Well, you might be surprised to hear it pops up in the world of complex geometric shapes.
Hold on. We went from ancient fractions to prime numbers, and now we're talking geometry.
Yeah, it might seem like a leap, but Sylvester's sequence actually helps mathematicians construct some pretty wild shapes. They're called Sasakian Einstein manifolds.
Sasakian Einstein.
Man,
Manifolds. Okay, you lost that.
the name's a mouthful.
Can we back up a bit?
Sure. Think of a sphere. You know, perfectly round.
Yeah, I get that.
Well, Sasakian Einstein manifolds, you can think of them as like generalizations of spheres.
Okay.
They're more complex, they have more structure,
Right.
but they still have that same kind of spherical quality in a way.
Okay, I think I'm getting a vague picture in my mind. But how does Sylvester's sequence even fit into all of this?
Well, the details are pretty technical,
Yeah.
but the key is that the rapid growth of the sequence that helps mathematicians prove that there's a huge number of different Sasakian Einstein manifolds out there, especially in higher dimensions.
So this sequence of numbers, as simple as it seems, is helping mathematicians explore like higher dimensional geometry.
It is. It really shows you how connected different areas of math can be, you know? What seems purely abstract one minute can have applications in a completely different field the next.
Absolutely. You mentioned applications in computer science too.
Right,
Now that feels a little bit more down to earth.
right.
So where does it show up there?
Well, Sylvester's sequence, it turns out, it pops up in algorithms,
Okay.
particularly the ones that are designed to like pack objects efficiently or find the best ways to cut materials.
Okay, give me an example. How does that even work?
Okay, imagine you're designing an algorithm to pack boxes into a truck.
Right?
I-
You want to avoid any wasted space.
Yeah, make it as tight as possible.
Exactly. Well, Sylvester's sequence can be used to create these really difficult packing problems,
Oh, okay.
to really test how efficient your algorithm is.
So you're using those massive numbers from the sequence
Yeah.
to represent like all these different box sizes.
Yeah, kind of like a stress test for the algorithm.
Right. If it can handle these super weird cases, it's probably going to be pretty good in the real world.
That's the idea. And the same principle applies to cutting problems too, you know.
Yeah.
Like if you're cutting fabric or metal from a big sheet, You want to minimize waste, get as many pieces as possible.
Right.
Sylvester's sequence, same thing. You can use it to create those tricky test cases again to really push those cutting algorithms to their limits.
That's so cool. So we're using like the unique properties of this sequence, the growth, the coprimality
Mm.
to really like challenge and improve these algorithms. This is incredible.
Yeah, pretty neat. We've gone from ancient fractions to like the frontiers of computer science, all thanks to this one sequence. I need a minute to process all of
It's
this.
a lot, right? But there's one more fascinating aspect I think we should discuss.
Okay.
And it takes us back to those prime numbers we were talking about earlier. And it raises some really profound questions about their distribution and patterns.
Okay, yeah, prime numbers always seem to have a certain mystique. What kind of questions are we talking about here? All right, let's talk prime numbers. You were saying that Sylvester's sequence raises some interesting questions about them.
It all comes back to that property we talked about earlier, how each prime number can only divide one number in the whole sequence.
Yeah, right. That was key to proving there are infinitely many primes, because each new number could bring in a brand new prime factor we hadn't seen before.
Exactly. But it also hints at a deeper connection, a connection between Sylvester's sequence and how primes are actually distributed.
Wait, so you're saying that this sequence, as weird as it is, might actually give us clues about how prime numbers are spread out among all the other numbers?
It's a pretty wild thought, isn't it?
It is. I mean, that's a bold claim.
Well, think about it. Primes are essential for understanding numbers.
Yeah, they're like the building blocks.
Exactly. But figuring out how they're distributed, that's been a puzzle for mathematicians, like, forever.
So we have the sequence where every prime can only show up once as a factor.
Right.
It makes each number in the sequence unique in that way.
Mm-hmm.
Could studying how those prime factors are arranged,
Yeah.
could that give us some insights into how primes are spread out in general?
That's the big question. It's like we have this special filter, the sieve, that picks out primes and puts them in this specific order dictated by Sylvester's sequence. And by studying that order, well, who knows what we might learn.
That's incredible. It's like this sequence, which seems kind of random on the surface, is actually holding on to some secrets, some hidden code about primes. So, I mean, this has been an incredible journey, hasn't it?
It has.
I mean, we started with what seemed like a pretty straightforward sequence.
Right. Multiply and add one.
Yeah. And we ended up exploring ancient fractions, proving there are infinitely many primes, finding links to geometry and computer science, and now this incredible possibility of understanding prime numbers better.
It's amazing how much depth there is to the sequence, right?
Absolutely. I'm leaving this deep dive with a whole new appreciation for Sylvester's sequence. I'm going to have to revisit those sources you gave me.
It's been fun exploring it with you. And hey, who knows? Maybe you'll be the one to crack the code and discover the next big thing about Sylvester's sequence.
And if I do, you can bet I'll be sharing it right here on the deep dive. So that's it for this deep dive into Sylvester's sequence. I hope you all enjoyed it as much as I did. Until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of knowledge.